Thank you all for coming. Before I get started, I know that some of you are wondering what the purpose of this talk is. Why are you all here? Instead of dissertation defenses, Berkeley Computer Science does dissertation talks, which is a way for me to share the results of my dissertation with the public. If you don't know, a dissertation is a collection of work that supports a single thesis. That thesis is a new piece of human knowledge. A tiny piece, but a new piece nonetheless. With this talk, I am formally sharing that new knowledge with the rest of humanity, aka you all. This talk is also a milestone in the life of a PhD student. This is a rite of passage marking the end of my PhD and the beginning of a new phase of life. So we're here to learn something new and celebrate the end of my PhD. With that, let's get started. In this talk, we will discuss how to make it so that any of you can walk into any smart space, like a smart home, and immediately start using it, even if you've never seen it before. We'll talk about why that's hard now and how we can make it better. There's a computer science joke that has a few versions, but the original quote is, "There are only two hard things in computer science, cache invalidation and naming things." In this talk, we're going to be talking about naming things in the context of smart spaces. People have been talking about smart homes and smart buildings for ages, but recent advances in low power networking and cheap computation have led to the emergence of smart devices onto the home market. These days, every Best Buy and Home Depot and Lowe's has a smart home section. Juniper Research estimates that there will be over 40 billion IoT devices by the end of 2021. The question is, how will normal, everyday users use the Internet of Things? To make this question concrete, I want to walk you through a quick history of IoT interfaces. In the beginning, there was the light switch, and the light switch was good. Anyone who entered a room could see it and know that they could control a light this way. And then came additional functionality like dimmers and LED light bulbs. And then we started using smartphone apps to virtualize switches and dimmers and buttons and other physical interfaces. And that was a good thing because lights started getting weird capabilities, like being able to change hue and saturation or strobe and scroll through colors. Sometimes with an app or firmware update, suddenly the same lights would have new capabilities. So these flexible software interfaces have some significant advantages over the physical light switch. This brings us to the living room I had many years ago in Ann Arbor, Michigan, shown here. As a smart home enthusiast, this room of course has a number of consumer IoT devices in it. Here you can see the locations of all the smart lights and which brands they are. There are 11 lights and 4 different brands. Each of these brands has its own smartphone app for interacting with the light. But of course, I don't just have lights. I also have motion sensors, door sensors, temperature, humidity, pressure, and light sensors. I have Sonos smart speakers, and of course I have an Amazon Echo. So how did I control all of these things? Sometimes I used one of the brand-specific apps to directly control a specific device, usually to take advantage of brand-specific functionality. Sometimes I used a universal controller app like SmartThings that integrates multiple brands of devices into one app. These apps also tend to provide templates for basic automation routines. Usually though, for automating behavior, I used a data-oriented interface like IBM's Node-RED. So here, sensors stream data to topics, which you can wire together into processing pipelines that ultimately send control data back to actuators like lights. But most of the time, for daily use, I used Alexa. So I had many different interfaces that I could use to interact with all of my smart devices, and that was great until I had visitors. The red couch has a pull-out bed in it, so when guests would come and stay in our living room, this was their bedroom, and they needed a way to turn off the lights after I left them alone to go to bed. Asking guests to install and configure these apps, or even just a single universal controller app, was right out of the question. The only thing that made sense was to use Alexa. But Alexa also has a problem. If this is what you see as a guest when you walk into a room, it's really unclear which of these things are smart things that Alexa can control. And even when guests know that something is a smart device, it's not clear how to refer to it. Because each one of these things, and sometimes groups of these things, have proper names that Alexa understands, which come from what I named them during setup. That works great for me because I set them up, But the problem is that if guests can't figure out how to turn the smart lights off, they unplug or switch off things manually, which kills power to the devices, and then none of my apps or Alexa or automation routines work. So I had to manually write down on a sheet of paper all of the commands that a guest might want to say to Alexa. We found it so useful that we kept this sheet around and pulled it out for all of our visitors. This state of affairs is not ideal. And I'm not the only one who has this problem. Here's a tweet from an Airbnb host who writes, like 1/3 of my Airbnb's binder are instructions on what specific words control which specific lights and exhortations to please not use the actual physical light switches. You can see on the note that it describes which appliances can be operated, including that Alexa does not turn on and off the TV, and provides examples of specifically what you need to say, like turn on bedstand light and turn off small lights. So what's going on here? The problem is that to use these interfaces, you need to know one, that a device is or is not smart, and then two, know the proper name of that device in order to invoke its functionality. So this is true for smartphone apps. Just because you have the list of device names in front of you doesn't mean that you know which one is which. And it is especially true for an intelligent assistant like Alexa. So most people interact with intelligent assistants using voice, and that gives you very few hints about what device names they know, much less which devices have which names. So why does this matter? It's kind of annoying, but we have our workarounds, right? Well, in a future where these technologies scale and become ubiquitous, you'll have to figure out how to use smart spaces that you've never seen before and may never see again. Imagine walking into a smart conference room right before an important presentation and trying to use it. In commercial spaces and public spaces, the building manager that set up that system will not be there to help you like they are in smart homes. Additionally, as technology improves and the numbers of mobile devices increase, the capabilities of a room may change dynamically from moment to moment. So, users will need to be able to walk into an unfamiliar smart space and quickly discover on their own what is possible and not possible to do in the space and how to achieve their goals. When a system supports this, we say it has discoverability. So in this talk, the first thing that we're going to do is understand how bad this problem is. There are two subproblems with proper device names. The first is the device-centric approach that underlies it. By device centrism, we mean representing the system to the user as a collection of smart devices. We do a comparative study of different ways of presenting smart spaces to users and find that a device-centric interaction framing really limits what users think the system can do before they even have their first interaction. The future value of IoT comes from interoperability between devices and the ability to support multiple applications, automation, and personalization. So if users don't even think of those applications because of the way the system is presented, that's not good for adoption. The second subproblem is proper names themselves. We run a guessability study to see how guessable device names are and find that even the best names are very difficult to guess. This is for several reasons that are due to the inherent nature of smart spaces. After characterizing the problem, we will propose and evaluate solutions, our goal being to achieve interactions in unfamiliar smart spaces in the first attempt. So first, we find in our comparative study that if you add intelligent assistants on top of the device representation, like Alexa, it does help mitigate the limited thinking of device centrism. So thinking long term, we're going to make sure that the interaction framing of our solution is centered on intelligent assistants. But most intelligent assistant interactions are done with voice, and voice makes the proper names problem extra hard because there are no good cues. However, if instead of speaking to assistants, we message them, now we're in the visual domain and we can use visual discovery aids. In particular, we're going to look at autocomplete and augmented reality. With our approach, all you need to know is how to message, and any one of you can have seamless interactions in new smart spaces that you've never been in before. This all brings us to my thesis statement. Now, I know that there are a lot of formal words here and a lot going on, but this is the core of the talk, so we're going to step through it piece by piece. The claim is that we can support end-user discovery in unfamiliar smart spaces while preserving an assistant-oriented interaction framing, By borrowing the following patterns from human to human messaging and applying them to human to assistant communication. Text messages composed with the aid of autocomplete, and photo messages enhanced by augmented reality. This will allow users to learn what functionality is and is not available in the whole space and invoke their target with a single interaction. And so that's our goal. So for the rest of our talk, we're going to characterize the problem, look at device centrism and proper names, and then we'll solve the problem. First, we'll look at just adding autocomplete, and that will get us part of the way there. And then we'll add augmented reality to autocomplete, and that gets us all the way to our goal of one-shot interactions in unfamiliar spaces. I'll summarize and end the main talk, and at the very end, I'll take a little bit of time to reflect on the PhD. So let's talk about how we present systems to users. Existing smart space interfaces are mostly device-oriented. The smartphone app approach, which is the default, is entirely device-centric. It presents the system as a collection of smart devices, aka devices connected to a network. Intelligent assistants like Alexa are also device-oriented, but they frame the interactions around an intelligent assistant who can control those devices for you. So this is like an assistant-mediated device orientation. However, there are alternatives, such as taking a data-centric approach. So these approaches could be either pure data, like Node-RED, where you read and write to data streams to interact with the system, or following the pattern above, data as mediated by an assistant. Now, there aren't really data-oriented smart home assistants that, for example, focus on brightness instead of the lights. So I put this cute data robot here to represent it. We propose a framework that organizes these different interaction framings along two axes. The first axis is how they represent the capabilities of the space. Are the capabilities represented as devices, or are they represented as data that you can read and change? The second axis is how the system is personified. If it's not personified at all, we call it unmediated. If it's instead represented as having an assistant that sits between you and the capabilities, we call it assistant mediated. Given that there are these different approaches to presenting a smart home system to users, the question is, how do they affect what the user thinks the system can do? What kinds of interactions the system supports? For example, if you use one interaction framing, maybe users will want to do a lot of automation. But if you use another interaction framing for the exact same system, automation doesn't occur to users at all. To find out how different interaction framings affect what users want to do, we ran a comparative study. We presented the same hypothetical smart home in 4 different ways and saw how what people wanted to do changed depending on the presentation. This is a significant departure from prior work. Past work on smart home interfaces has focused on getting at how people naturally conceive of smart spaces and has tried to avoid biasing or priming people with anything specific, though the prompts are usually biasing anyway. We say the real system will be biasing, and we should embrace that and incorporate it intentionally into our system design. And that means understanding how different framings affect users differently. To compare these framings, we came up with a hypothetical smart house with a certain set of capabilities. We then represented those capabilities in 4 different ways in questionnaires that we sent out to Mechanical Turk. If you don't know, Mechanical Turk is an online service that allows people to do small tasks for small amounts of money and is commonly used to recruit research participants. The way we define the smart home's capabilities is that we chose a list of common consumer smart devices that you can buy in a store. That list of devices became the devices part of the framing. And then for each device on the list, we converted the device into equivalent data streams. For example, a smart light bulb in the device list might be converted into data streams like brightness, color, warmth, power that users can access or change. So here's the structure of the 4 questionnaires. For the unmediated prompts, we asked users to pretend that they lived in a hypothetical smart home, and we provided either the list of smart devices or the list of equivalent data streams, and then asked participants to write for 5 minutes about what applications they wanted in their home. For the assistant-mediated prompts, we asked people to pick a male, female, or androgynous voice and name for their smart home AI, and then provided them with the same list of devices or data, which we said the assistant had access to, and then we began the prompt with OK AI name. The purpose of the personalization was for users to feel a sense of trust and rapport with the assistant right off the bat. The important thing here is that it's the same smart home capabilities in all four cases, just represented in different ways. We received over 1,500 responses, ranging from about 300 to nearly 500 for each prompt. So we've got the data. How do we compare the effect that the different prompts had on participants? The first thing we do is compare the qualitative differences between the answers. Responses to the unmediated devices prompt tended to talk about what devices they wanted. The unmediated data prompt tended to talk about monitoring things. The assistant mediated prompts had a lot of immediate remote control style commands, but also a lot of automation routines. The second method we used was to calculate statistically key words. Now, there's a lot going on here visually, but it's not important. I'm just trying to convey the method. We used a chi-squared statistic to determine which words were more associated with responses to one prompt versus the others. So we looked at the most key nouns, verbs, and everything else. The final method we used was to label answers with the type of operation they are to create profiles of user operations for each response. We developed a set of 9 labels, 2 of which are shown here in this example. Once we developed the labels, we had 3 independent annotators go through and label the participant responses independently. The Cohen's-Kappa measures of inter-rater agreement were between 0.76 and 0.78, which means that the annotators tended to pick the same labels independently, which in turn means that our labels were good and clearly defined. So what effects did the prompts have? Unmediated devices, which is the most common interaction framing found in smart homes today, resulted in pretty limited expectations of what the system could do. When looking at the operation profile, which is shown on the right with the 9 possible labels, you can see that by far the most common response to the unmediated devices prompt was to express a desire for a device. We asked people to write about what applications they wanted in their smart home, and people given this framing said, I want this device, I want that device. So participants given the unmediated devices prompt confused having a device with a smart home application, considering them equivalent. Additionally, we can see that the next most popular kind of response was wants remote control, and that statistically keywords associated with this prompt more than the others were sensor, phone, and device. This all suggests that the main interaction method envisioned here is one-on-one manual interactions where the person uses a smartphone to manually operate individual devices one at a time. Perhaps related, we also see a low percentage of responses mentioning automation. We're not showing the operation profiles of the other 3 interaction framings here, but they all have more automation than this framing. It has the lowest automation out of all 4 prompts, which is wild because this is the most common interaction framing used in smart homes today. And yet, it seems to result in people viewing smart devices as isolated islands of functionality that don't necessarily interoperate. Conversely, in the assistant-mediated devices prompt, we add an assistant who can access the devices, the same set of devices. Everything else is the same, except now there's an assistant. And what we find is that the percentage of responses that mention automation nearly doubles. The keywords that are more statistically associated with this prompt include conditional words like when and if that are indicative of automation. So we hypothesized that adding the intelligent assistant was able to provide a notion of global computational scope to the system so that in people's minds, the assistant connects the devices together and provides some autonomous agency. We had many other interesting, though more minor findings, which are in the dissertation if you're interested. The main takeaway here is that if we're trying to help get these currently device-oriented technologies adopted and scale into the future, we should at least present the systems with an intelligent assistant on top of the device framing to help people see the potential of these systems to do automation routines and device interoperability. We'll come back to this takeaways slide later. We're going to build it up throughout the rest of the talk. So that was digging into the device centrism part of the proper device name paradigm. Next, let's talk about proper names. Proper names are hard to guess, and this has come up in computing systems before. There was a famous 1987 paper by George Furness, who's actually now a professor emeritus at University of Michigan, about the difficulty of guessing names of system resources. We have this problem in the command line, databases, and file systems, to name a few. The way we solved these issues in the past was by using a graphical user interface and mouse that allows users to point at things they want to interact with instead of typing their exact names. And more recently, we've seen these text-based search suggestion boxes like Spotlight on Mac or the Windows search bar, which help us find things when maybe we have just a partial idea of what they're called. The solutions we end up coming up with in this talk will in fact parallel these two solutions. Picture photos with augmented reality end up serving the same role as GUI and mouse, and autocomplete acts like the search bar, but with our own distinct twists for helping people discover new capabilities. But before we get there, let's ask, can we just solve this problem by naming things the best names? In some of our experiments, users suggested that we just name devices better. Would that work? The answer is no, but let's find out why. We created a smart conference room simulation with a bunch of different smart lights, which are circled in the picture on the left, and non-lights like a projector and blinds, which are circled on the right. Excuse me. We crafted another Mechanical Turk task saying that a building manager had named these devices their most guessable names. Workers would see either this image with the light circled or the image with the non-light circled, and then answer these questions, where we ask them what they thought the most commonly guessed name was for the circled devices. So in this way, we collected 100 names for each device or device group. So what did we find? We found that projector was the only guessable name. 75% of the names for the projector were exactly the name projector. However, 94% of names for the projector contain the word projector somewhere in it. So if you just look for that keyword, which for example Alexa does, then you're good to go. However, all the other devices were in much worse shape. This chart shows the popularity of the most guessable name for each device. So on the left, you can see the most popular name for the device in quotes and parentheses, and the bar shows you what percent of the 100 names were that most guessable name. You can see that all of these names are less than 30% of the submitted names, sometimes a lot less. This means that if you name these devices these names, which are the best possible, most popular names, a new user in the space would still have between a 70 to 95% chance of being wrong on their first guess. This is consistent with Furness, who looked at many domains and found that even the most popular names tended to be around 20% of the total names. Now, you might notice something else about these names. 3 different devices or device groups are called blinds, and 2 different device groups are both called spotlights. This brings us to our second problem. There's significant overlap between the top names. So here you can see the top 5 names submitted for each device. And here, all the names that are still visible show up in the top 5 names of at least one other device. So poor spotlights in the middle there, any of its top 5 names could also refer to other devices in the room. Furness called this precision, meaning when 2 different people use a name, how often are they referring to the same object? They found that this problem varied by domain, and we show that smart space device names just happen to fall on the particularly bad end of the spectrum. So the most important takeaway here is that we can't just name things the best names and hope people guess right. We have to have some kind of discovery aid. So that was it. We've characterized the problems with proper device names. And that helps gives us some guidance in shaping our solution. Our first solution, which involves autocomplete, will get us part of the way there, and augmented reality will give us the rest of the way. So let's take a crack at a solution. Our goal is to help users figure out what kinds of interactions are available in a smart space, aka what devices are available and what they can do, and what their proper names are. And we want to do this within an intelligent assistant interaction framing. The problem is, most intelligent assistant interactions are over voice, and it's hard to provide cues over voice. Is there some way to basically take this note and put it in an automated tool? Well, if we have users message intelligent assistants, we can use autocomplete, which would basically take that note and work it seamlessly into the user's interactions with the assistant. Obviously, voice has hands-free advantages that you would lose by going to messaging, but the idea here is that you can't use voice anyway, so you would use this interface for one, two, maybe three tasks in a new smart room because it has this autocomplete discovery aid. But then you'll have learned about the other devices in the room and what they can do from the autocomplete suggestions while achieving your main tasks, almost subconsciously. So, this knowledge that you've learned about the room more broadly would allow you to use other interfaces like voice that don't have discovery mechanisms. So, the goal for autocomplete here is to help people accomplish their tasks, but also to learn about the rest of the stuff in the room as quickly as possible. This is the discovery component. Most autocomplete in our lives is not designed for discovery. Autocomplete, as described by Google, is about predicting what you already planned to say to cut down on typing effort. This makes sense when you're Google because you can assume that what the user is looking for is there because the internet is big. You're just helping them find the needle in a haystack faster. But that's very different than helping people discover the entire finite set of things that are available. So the question is, are some autocomplete designs better at balancing accomplishing specific tasks quickly with encouraging broader discovery? We came up with three different dimensions of autocomplete designs that we thought would impact discovery. Combining these dimensions together gave us 8 different designs. However, I'm not going to go into them in detail in this talk because, as we'll discuss shortly, our study didn't find many significant differences between the designs. To evaluate our designs, we developed an online testing platform that would help us get a lot of evaluation data because we had so many interfaces. We made a simulated conference room, which should look familiar, and a simulated smartphone with a chat messaging interface to an intelligent assistant named Scarlett. We sent our study out to Mechanical Turk again. When Turkers clicked on the link, they were randomly assigned one of our autocomplete interfaces, or they would get no autocomplete at all as a baseline condition for us to compare against. Participants were asked to perform 3 tasks. We showed them pictures of the goal state to avoid biasing them with words. For each scenario, they could review the goal state at any time by pressing the button that you see at the bottom here under the room. It would render the goal state on top of the room, and then when they released the button, it would go back to the way it was. Users could choose to be done with the scenario and move on at any time by pressing the button on the bottom right under the phone. So we asked people to do 3 tasks or 3 scenarios. The first scenario involved a device with an easy to guess name, the projector. So even users without autocomplete should have a good chance to get this one. The second scenario involved a hard to guess name, the front lights, where we would expect that autocomplete would come in handy. The third scenario showed a goal state that was not possible. So, this scenario represents when you have a goal in mind, but the device that you want to control is not actually connected. Many smart spaces have a mix of connected and unconnected appliances, so it's critical for discovery that users can tell when a device is not smart. So, we told users in every scenario that some goal states may not be possible and that they could move on when they thought that that was the case. We evaluated the autocomplete designs on a number of metrics. However, what we're mainly interested in is how well the designs balance helping the users accomplish the specific task versus learning about the rest of the capabilities. To measure task completion, we looked at user accuracy, which is to say how many of the scenarios did the user get right. There were only 2 scenarios where the goal state is possible, so users could achieve an accuracy of 0, 1, or 2. To measure learning, we had users take a questionnaire right after completing the scenarios. The questionnaire asked 3 different kinds of questions to assess learning. The semantic questions showed a picture of the room and asked whether it was possible to put the room in that state. The lexical questions posed example messages with different proper names and asked whether Scarlett could understand it. And the grounding questions asked whether the indicated devices were controllable, and if so, what were they called? Most of these questions involve devices that are not involved in the scenarios, so they should assess this broader discovery that we're interested in. We found that any autocomplete was better than no autocomplete. However, as mentioned previously, we didn't find many significant differences between the autocomplete designs. So for the next few slides, I'm going to combine all of the autocomplete data together. So we can see here, autocomplete helped users accomplish tasks and learn about the room compared to users without autocomplete. So these graphs show the distribution of results for users of autocomplete versus those without. The orange lines are the median results, and the blue dots are the mean or average result. In the first graph, we can see that autocomplete users were able to achieve the goal state in more scenarios. The second and third graphs show that autocomplete users also learn more about the room, including what states it could be in and what proper names are understood by Scarlett. Let's dig into these scenarios a bit more to see what was going on. In the easy to guess scenario, 82% of autocomplete users were able to achieve the goal state, compared with 69% for users without autocomplete. The graph shows that autocomplete users also tended to do it in fewer submissions. In the hard to guess scenario, we see bigger differences. 67% of autocomplete users achieved the goal state, while only 25% of users without autocomplete did. The autocomplete users again tended to do it in fewer submissions as well. Though you'll note that we did not achieve our goal of having autocomplete users accomplish their goals in only one interaction. The impossible scenario, however, really caused everyone to struggle. Since this device isn't connected in the simulated conference room and the goal is impossible, the ideal result is that users decide to move on after 0 submissions. The idea is maybe autocomplete users would look at the list of device names available and see that there's nothing there that matches the description of this big ambient wall light and move on. Well, that's not what happens. Autocomplete users on average make about 10 trial and error guesses, sometimes a lot more. In the transcripts, it looks like users go through all the light commands until they try turn on the lights, which turns on all the lights except this one since it's not connected. At that point, they usually give up and realize it's not possible. My hypothesis is that this is the reason we don't see any differences between the autocomplete interfaces. Any differences in helping people learn through autocomplete suggestions are wiped out by the fact that all the users end up trying everything anyway during this scenario and learn everything that there is to know about the room. So, if you give people a list of all the smart devices in the room through autocomplete, it does not solve the discovery problem. We saw that even with autocomplete, users still can't accomplish hard to guess names in one attempt, though it's better than no autocomplete. And people still cannot tell whether a device isn't working because it's not connected or because they just haven't guessed the name yet. These remaining issues are due to what Furness called the precision problem, where the same name could apply to multiple devices. The important takeaway from this study is that autocomplete is an improvement, but not enough on its own. Okay, so next, we're going to explore adding augmented reality to the mix. To solve the precision problem, what we need is a way to map the proper name of a device to which device it is. And the method that we use should still fit within this whole sending messages to intelligent assistants interaction framing. So here's an idea. Let's label the smart devices with their names in augmented reality. We can keep this in a messaging paradigm by modeling the interaction after Snapchat. For those of you who don't know, Snapchat is a messaging app built around photo messages. You open the app to a camera view and you can look around, snap a picture, caption it, and then send the captioned photo to friends. Except in this case, we're going to send it to the Smart Space Assistant. I developed an implementation of this called Articulate. Articulate is an Android app that uses Google's augmented reality libraries. So here's what it looks like to users. First, you'll notice off-screen location markers around the sides of the screen that direct the user to smart devices in the room. As you move, they slide around, helping you navigate. When a device is on screen, you can see this animated glowing ball of light indicating that this device is connected, and you can see its proper name hovering over it. If you take a picture, you can caption the photo and get autocomplete suggestions for your caption. The autocomplete provides suggestions for whatever devices are in the picture. These suggestions are actually quite helpful, especially for color. Alexa understands over 145 different specific color names, which is why there's a show more options option. It turns out that devices aren't the only thing with proper names. When you send the message, it gets sent to Alexa, a chatbot clone of Alexa that I wrote because the real Alexa does not accept text input. The message you send is shown in the conversation history view along with Alexa's responses. You can also send messages directly to Alexa there in the chat without autocomplete. And you can switch back and forth between the chat view and the camera view whenever you want using the two icons at the bottom of the screen. But what's a smart space interface without a smart space? We created a small smart home testbed with lamps, a door lock, and a sensor. The smart home can be controlled by either Alexa through an Echo Dot shown on the far left, or by our Alexa chatbot clone through Articulate shown on the far right. Now, evaluating an augmented reality interface for unfamiliar smart spaces is a really tricky thing to do during a global pandemic where people are told to stay in their own homes and avoid interacting with strange researchers. So we got creative. All of my lab mates in Lab 11 registered as part of my study team and got human subject training. And we used a form of snowball recruiting to recruit participants who already lived in the same households as my colleagues. I made a no contact delivery of the smart home testbed, phone with the Articulate app preloaded, and other useful things. The Lab 11 member on site set up the smart home testbed with my help over Zoom. Next, the on site facilitator configured Articulate by making an augmented reality scan of the new smart space while screen sharing the phone with me over Zoom. This involves scanning the whole area from different angles to build up an augmented reality map, and then tapping the devices on screen to place a marker and label them correctly. When complete, the facilitator brought in the participant and we began the session. We repeated this process 9 times, including a couple 4-hour driving days and a cross country shipment. All sessions started with a pre interview where I asked the users about their prior experiences with relevant technologies. Then, users began the voice interaction phase where they interacted with Alexa using voice. This establishes a baseline for how hard it is to use voice to accomplish the tasks in our study. Then, the room is reset and users are given the Articulate app. They then go through the same tasks as before, but now with the app. After that, there's a final voice interaction phase where the users interact with Alexa again using voice, and we can see what knowledge they've retained. At the end, we'll have users fill out a system usability scale questionnaire, and we have a debriefing interview where we ask them questions about their experience. We also had a second session protocol that skipped the voice phase entirely and started with Articulate right off the bat. So this was to avoid the learning effects from the voice phase. We randomly assigned users to one of these two session types. We had 5 different tasks that we asked people to do. The first task involved a device with an easy to guess name, door, this set a baseline. The second task involved a hard to guess name, mood lamp. The third task was impossible, so this lamp did not have a smart bulb in it. We told the users frequently throughout the session that some tasks would be impossible and that they could move on whenever they would like, so the goal being that they would figure this out as quickly as possible. We also had a sensor in the room called multi-purpose sensor. It measures multiple things, but Alexa only exposes temperature from sensors at the moment. We told users that there was a device in the room that measures something and to get the current value from Alexa. So we asked all 4 of these same tasks in every interaction phase. To avoid biasing users with language, the on-site facilitator would say something like, ask Alexa to turn on this device for you while using a laser pointer to point at the relevant device. In the final voice phase, we also asked a new task, which was to turn on light A. So light A was installed somewhere in the space in a light that is normally in the room. So we swapped out the usual bulb and installed the stealth smart bulb. So the idea was to see whether users would discover it using Articulate, even though there are no tasks involving it, and then remember it later when we ask them to interact with it during the final voice phase. So how did the interfaces do? Here you can see the number of attempts each user made for the different tasks using the voice interface. The red background shows when the user didn't achieve the goal, and the yellow background shows when the user found a way to accomplish the goal without using the proper name. As a baseline, you can see that overall, voice users had a hard time completing tasks in an unfamiliar smart space. Everyone was able to unlock the door in one attempt. Some users were also able to eventually get the hard to guess name because Alexa will sometimes suggest a device name if she's not sure what you're referring to and what you've said is close enough to something she knows. However, when it comes to task 3, people struggle to know when it's not connected versus them just not guessing the right name. Participant 1 was a trooper with their 28 attempts. The sensor task was the most difficult. As one user put it, I have to figure out where this device is and then guess what it's called and then figure out what it measures. Sensors are a very difficult problem, and so the voice user struggled. Articulate, on the other hand, worked. Whether the user started with voice, which was participants 1 through 5, or started with articulate directly, they were largely able to achieve the goals in one attempt, even the sensor task. As one user put it, I never would have even seen the sensor without the app. And for the not connected device, task 3, we see the holy grail of 0 interaction attempts. The two users who did interact once both said out loud that they didn't think it was connected, but that they would try interacting anyway. So this is a resounding success, and we can see what an improvement it is compared to voice. Voice is on the top with its many guesses and failed goals, and articulate is on the bottom with one-shot interactions and 0 interactions with unconnected devices. As a bonus, the knowledge learned during articulate also translated to the final voice phrase. After putting the app down, users were largely able to retain what they had learned and accomplish the tasks using voice. Users were even able to accomplish task 5, the new task involving Light A, even though it was the first time we'd asked users to do that task and they didn't have a discovery mechanism interface right in front of them. You'll note, however, that the sensor remained difficult. It's a long command that has to be phrased exactly right. Turn what is the temperature according to multi-purpose sensor. However, there was also a lot of resistance to remembering the name of the sensor itself. Multiple people stated that they didn't think that they should have to specify the device name since they're just interested in the temperature, and also there was only one sensor, so Alexa should be able to figure it out. Interacting with sensors could be a use case that just doesn't line up well with Alexa's device oriented interaction framing and where a data centric framing might have less friction. The most important takeaway here is that we did it. Adding augmented reality labels to autocomplete got us to one shot interactions with intelligent assistants in unfamiliar smart spaces. So let's circle back around to that core thesis statement to make sure that we have justified all the parts of our claim. We can support end user discovery in unfamiliar smart spaces while preserving an assistant oriented interaction framing. And we did it by taking a messaging approach and using autocomplete to help compose those messages and adding augmented reality labels to photo messages. Users were able to then determine what functionality is and is not available, and they could invoke it with a single interaction. Dissertation defended. And if you'll indulge me, before I end, I'd like to reflect briefly on the PhD. I presented my dissertation in a linear fashion, but as many of you know, that's not at all how research goes. A lot of the PhD doesn't make it into the dissertation. There are successful published projects that don't fit in with the thesis, as well as not so successful projects. Young PhD students might be either relieved or alarmed to see how many failed starts and weird paths there are along the way. But it's more than just other research projects. A PhD is also shenanigans, like getting access to secret places around Michigan's campus, 3D printing keys for research, secretly turning the NanoFab's LED wall into a multi-story Nintendo simulator, hacking BBB, the CS building's lights, building an Android app to control them from anywhere, flying Icarus, the inflatable shark, around the CS lobby, blowing up a light switch and half the fourth floor lights with it, rescuing Professor's drone from the top of the building, and so many more. And art. An intrepid group of students secretly installed a 4-story programmable light sculpture on the Michigan CS building's spiral staircase one night as a prank. People anywhere in the world can write a light show for the staircase in JavaScript in the browser and submit it to the website. We took the lights down, the department asked us to put it back up for visit days, and then it stayed up, and then it failed fire code. And then the department paid to bring it back into code and make it a permanent installation. I did a lot of outreach during my time, but closest to my heart is the CS Kickstart Summer Program that I founded at the University of Michigan, which is still going strong to this day. The 9 months that I spent developing that program were some of the most hectic and formative of my time at Michigan. And of course, there's friends, lots and lots of wonderful friends going on adventures together. I couldn't have done any of this without support from my amazing advisors. Prabal, who taught me how to write, supported all my crazy research directions, and ran interference with law enforcement at least once. And Mark, who has patiently met with me weekly for the last several years, helped me navigate HCI as a newcomer, and ultimately made me feel like I belong somewhere. My dissertation and quals committee members, Bjorn, Marty, and Dan, gave me invaluable advice towards the end of my PhD. At the beginning of my PhD, Quentin Stout at Michigan was my advisor for my first year after my original advisor went on paternity leave. I could have easily fallen through the cracks that first year, but Quentin invested time and energy into my well being, including weekly coffee chats. Alex Halderman and his group brought me into the security researcher family, where I got to travel to interesting places and meet interesting people. They don't usually attend these talks, but I want to shout out to university staff in general and Kelly and Shirley in particular. At Michigan, it's Kelly who fought to have the department make the staircase lights a permanent installation. Uh, she supported CS Kickstart and helped in 100 other ways. At Berkeley, Shirley fortunately has not had to deal with our shenanigans as much as Kelly did, mostly, but she has been instrumental in helping us Michigan transplants transfer and graduate. And finally, I would never have done this without my family. This is a picture of me and my family in the early 90s at a barbecue with my mom's PhD advisor in oceanography. Both of my parents were scientists and taught me the importance of education: science, history, math, books, and later computers. Because of them, ever since I was a kid, I wanted to be a scientist. And now I can finally say I am. Thanks.